Hello everyone, this is Abdulrahman bin Rabia. I will be presenting today our paper, MSS Lightweight Network Authentication for Resource-Constrained Devices via Mergeable Stateful Signatures. There are currently 31 billion IoT devices that cover many aspects of our lives, from smart home to healthcare to transportation. In a typical IoT environment, IoT devices frequently send small messages to a single server or gateway, which need to be authenticated to stop various attacks. Particularly, quick authentication of such messages can be critical to saving lives. For example, patient data who has irregular blood pressure. Also, since IoT devices are often powered by limited rechargeable batteries, message authentication must not consume high energy. Traditional authentication using digital signatures solves this problem, but they are computationally expensive for IoT devices. As a result, authentication takes a long time and high energy. Therefore, an authentication solution that is efficient in the amount of computation and energy usage is needed for IoT. Our solution utilizes two things. Because the server is always the same party in IoT environments, it can keep state, and thus our scheme can do most of the work offline. Also, since IoT messages are usually small, our scheme creates the signature by only composing basis signatures corresponding to message characters. The table shows the improvements in speed and battery lifetime that we gain with MSS. The intuition of MSS is as follows. Instead of signing a message, we sign each of its characters following an encoding scheme. In case of binary encoding, we would sign the message string of bits. This allows us to prepare a pool of reusable signatures and assign each signature to a bit location and value. Therefore, when the device knows the message it wants to sign, say 101, it only uses the corresponding signatures from the pool. However, this introduces two issues. The final signature becomes too long, requiring high bandwidth. We utilize the homomorphic property to merge the signatures into a single signature. Also, if the adversary sees enough signatures, it can forge a new signature. To solve this issue, the scheme signs a nonce, which will also be merged into the final signature. This is a costlier operation, and importantly, it can be performed completely offline before knowing the message. Therefore, in MSS, once the signer knows the message, the online signing only merges already pre-computed signatures to produce a single signature, which is much more lightweight. To show how this works, the signer would keep a pool of signatures that correspond to different bit values and locations. For example, the first column has a pair of signatures. When a message has its first bit as 0, sigma 10 corresponds to its signatures. Otherwise, sigma 11 is used. Before signing a message, the message is converted into its binary representation and parsed as M1 through ML. And then each representative signature is fed into an efficient merge function. For security, we also merge in a non-signature that is already pre-computed. Then the final signature is produced. The traditional crypto function for digital signature has the form where the message is raised to a secret signing key. The crypto function has the properties that m to the k can alternatively be calculated using two steps. The first one is traditional signing by having the multiplicative factors that make up the message m independently raised to k. In other words, signing each factor of m alone. The second step involves multiplying the signed messages, the message factors. In other words, merging the subsignatures to compose the final signature. MSS utilizes this feature by making the first component completely offline, which is the heavyweight one. This is done by making the message follow an encoding scheme like binary, and then each factor of the message is represented by a random value that corresponds to a digit location and value. This allows our scheme to prepare a pool of signatures ahead of time. So in the online phase, only the signatures that correspond to the message are merged and multiplied together to produce the final signature. As mentioned earlier, for security reasons, we also merge in a non-signature. Since traditional signatures require exponentiation, the number of multiplications needed to produce a signature depends on the size of the exponent, which is the signing key length. Our scheme, on the other hand, multiplies the signatures corresponding to the message bits. This means that the number of multiplications is based on the number of L signatures being merged. Now, the size of L depends on the message size as well as the encoding scheme being used. For example, a message can be represented using hexadecimal using a smaller number of characters. We then show a concrete application of our signature scheme, which is two-factor authentication. 2FA is used to overcome password weaknesses, and so they are becoming popular. However, they require two-way communication, which might not be possible in IoT environments with intermittent connectivity. As a result, TOTP systems that produce one-time passwords are being used, as they require only one-way communication. We use our scheme to build two efficient TOTP systems that can be used for two-factor authentication. Public key cryptography can solve this problem, but it is too expensive. Our solution provides the same advantages with a lot of efficiency improvements, which is also competitive with other solutions like symmetric key cryptography, which has a security issue. Hash chains are another solution for this problem, but they have lifespan and they are expensive to regenerate a target hash. We implement MSS in the context of TOTP systems and compare it to other TOTP systems. Our RSA TOTP system reduces authentication latency at least 3 times compared to other systems. Our EC Al-Gamal system also reduces the authentication latency at least 2 times compared to all other alternatives. Also, our RSA TOTP system reduces the authentication energy consumption at least 3 times compared to TOTP systems. Also, our MSS EC Al-Gamal system additionally reduces the authentication energy consumption at least 3 times compared to others.